Let's investigate the Transmon creation and annihilation operators. In the previous video in the quantum mechanics playlist, I derived the Transmon Hamiltonian. In this video, I'm going to write that Hamiltonian in terms of the creation and annihilation operators. But first, I need to write down some important definitions. I'm going to define the dimensionless charge operator in terms of the creation and annihilation operators. So lowercase n with a hat denotes the dimensionless charge operator. This operator has been normalized. We've divided the charge operator by a factor of 2e, where e is the charge of the electron. So the reason we divide by 2e is because we're dealing with Cooper pairs in superconducting devices. So this quantity does not have any dimensions. So it is an operator associated with the charge. And let's write it in terms of the creation and annihilation operators. So we're going to have a prefactor, the imaginary unit I times Ej over 32 EC, all raised to the power of a quarter. And then we have the difference of the creation and annihilation operators. So I'm using a shorthand notation for these operators. This is the creation operator, and this is the annihilation operator. Another name for these operators are the raising and lowering operators. Collectively, they are known as the ladder operators. So this notation over here with a line at the top, that denotes raising, and this notation with the line at the bottom, that denotes lowering. So these are just like the operators that we were dealing with for the quantum harmonic oscillator. So this notation is a lot more convenient and it's faster to write. Now, I also want to define another operator in terms of the creation and annihilation operators. That is phi, the superconducting phase. So this is also a dimensionless quantity. We've taken the flux and we've divided by something that has units of flux. There's also a factor of 2 pi because this goes inside a cosine when we put this into the Hamiltonian. So both of these were discussed in the previous video where I derived the Transmon Hamiltonian. This one also has a prefactor, and the prefactor is 2 EC over EJ to the power of a quarter. But now we're taking the sum of the creation and annihilation operators. So over here we have the sum, and over here we have the difference. Now I want you to notice that there is no imaginary unit I over here. But over here we do have an imaginary unit I. What is the reason for that? Well, both of these correspond to physically observable quantities. So these operators have to be Hermitian. And if they're Hermitian, that means they have to be equal to their Hermitian adjoint. So if we take the Hermitian adjoint of this over here, this creation operator is going to turn into an annihilation operator. And this annihilation operator is going to turn into a creation operator. So these will actually swap positions. And that's going to introduce a minus sign. So we will get a minus sign over here. But luckily that minus sign is compensated for by this I. Because when we take the Hermitian conjugate of I, we get minus I. So we have a minus sign over here and a minus sign over here, and together they give a plus sign. So this is equal to its Hermitian adjoint, and that means it is Hermitian. This one over here, because we just have the sum, flipping these guys around is not going to change anything, because addition is commutative. So we have the commutativity of addition saves us, and this is a Hermitian operator as well. So both of these guys are Hermitian. Now, they have a very important relationship. So together they actually have a canonical commutation relation. This superconducting phase operator and this dimensionless charge operator, when we take the commutator, give I, the imaginary unit. And that is very important. This is analogous to position and momentum. This is playing the role of the position operator, and this is playing the role of the momentum operator. And there are similar definitions where you have the sum and the difference of the creation and annihilation operators for the quantum harmonic oscillator. One more thing that I want to write up here is the commutation relation between these operators. If we take the commutator of the annihilation operator and the creation operator, that gives 1. Or you can think of it as the identity operator. So it's important to have this order. This ordering is very important. First we have the annihilation operator and then the creation operator. Or you can think of it as the lowering and then the raising operator. If we were to flip these guys around, we would get a minus sign. We would have -1 over here. And I will be using this commutation relation later in the video. Now what I want to do is write down the Transmon Hamiltonian. So the reason for writing all these definitions out is because I'm going to substitute these into the Transmon Hamiltonian, and then I'm going to write the Hamiltonian in terms of the creation and annihilation operators. So let's do that. So from the previous video, I had a Hamiltonian of this form. H with a hat, that is the Hamiltonian operator, is equal to 4EC times this dimensionless charge operator squared plus EJ times 1 minus cosine of the superconducting phase. So have a look at what's going on over here. All I've done is I've actually added a constant. So this constant has no physical significance. Adding a constant to the Hamiltonian is just like changing the zero of the potential energy function. It doesn't have any physical significance, and so we're free to choose whatever constant is most convenient. In the previous video, I didn't have this constant over here. I just had minus cosine. But now I have 1 minus cosine. And the reason for that is it's going to get rid of a constant later on. But I just want you to be familiar with this. You're free to add and take away any constant you want for a Hamiltonian. So now what I want to do is do a Taylor series expansion on this cosine. So this is approximately equal to, this kinetic energy term is going to remain unchanged. We're still going to have 4EC n hat squared. But over here, I'm going to get a quadratic term and a quartic term. And then also higher order terms, but I'm just going to stop. I'm going to truncate that series at the quartic term. So over here I have EJ on 2 phi hat squared, and then minus EJ on 24 phi hat to the power of 4. And in the previous video, I also had a minus EJ that has been eliminated by adding this constant. So that is all I wanted to do. I started with this Transmon Hamiltonian, which was derived in the previous video, and then I performed this Taylor series approximation, and that's given me this. The first two terms are analogous to the quantum harmonic oscillator. We have something that is quadratic for the kinetic energy, and we also have a quadratic term for the potential energy. We can think of this as the momentum and the position. So these guys by themselves are going to have something that behaves like a quantum harmonic oscillator. And what do we expect for a quantum harmonic oscillator? We expect evenly spaced energy levels. But that's actually not what we have in this system. That's because of this quartic term. So you can think of this as a perturbation. We have a quantum harmonic oscillator with this quartic perturbation. That is just like the pendulum in classical mechanics, where you can describe it as a simple harmonic oscillator, but then as you move further and further away, that quartic contribution becomes larger. And if you move really far away, this quartic contribution is not enough, and you need higher and higher order terms. But for this video, I'm just going to consider this, because for the operation of the Transmon qubit, we're only going to be interested in energy levels that are close to the ground state in the first excited state. We're not interested in really, really high energy levels. One important thing that I want to write down is a convention that I'm using in this video. I'm using the convention that EC is equal to E squared over twice the capacitance. So I could also have taken this 4 and absorbed it into this constant, and I would have 4 over here. That is an alternative convention, which I have used in some of the previous videos. But in this video, this EC means this combination of parameters. And this capital C is the capacitance. So if we want to change EC, we just have to change the capacitance. We can't change the charge of the electron because that is a fundamental constant. But if we change the capacitance, we can change EC, and by changing EC, we can change the ratio of EJ over EC. And it is that ratio that has a very important physical significance. It changes a lot of the properties. And if that ratio is such that EJ is much larger than EC, then we're in the Transmon regime. So we're no longer dealing with a Cooper pair box or a quantronium qubit, we're dealing with a Transmon qubit. And that is what this video is about. So now what I want to do is substitute these definitions into this Hamiltonian. So let's go ahead and do that. What is that going to be equal to? So this approximation is going to be equal to, if I square n, this I is going to get squared, and that's going to give you a minus sign. So I'm going to get minus 4EC, and then I'm going to have to square this. That's going to give me EJ over 32EC to the power of 1/2. It's 1/2 because I'm squaring this quarter, and that's going to give me this half over here. So that's just a factor of 2 multiplying over here. That's 2 over 4, which is 1/2. And then I have to square this. That's going to give me the creation minus the annihilation operator squared. So that is the kinetic energy term. Now let's have a look at these potential energy terms. Over here I'm going to have plus EJ on 2 times this phi squared. So we're going to have 2EC over EJ to the power of 1/2 as well, because we're squaring this. And then we have the sum of the creation and annihilation operator squared. And then finally, we have that quartic term. So that's minus EJ on 24. This 24 comes from 4 factorial. This is from the Taylor series expansion. And then, because we're raising this to the power of 4, that cancels with this power of 1/4. So then we're left with 2EC over EJ. And there's no power because we've canceled it out. And then finally, we have the sum of the creation and annihilation operator to the power of 4. So this is what we have. We've just substituted it in. You can see this prefactor and this prefactor have the same fraction on the inside, but there's a different power. So let's have a look at what we've actually got. This coefficient over here and this coefficient are actually the same. If we bring this EC inside, that's going to become EC squared. And it's going to cancel with this EC in the bottom. So we're going to have EJ EC. And if we bring this 4 inside, that 4 is going to get squared, and it's going to become 16. So then we're going to have 16 on 32, which is 1/2. So that's actually going to give us this coefficient out the front. We're going to have the square root of EC EJ over 2. So this 4 becomes a 16, then 16 on 32 is a factor of 1/2. And what about over here? If we bring this EJ inside, it's going to become EJ squared. That's going to cancel with this EJ. And if we bring this 2 on the inside, it's going to become a 4. 2 on 4, that's also 1/2. So this prefactor and this prefactor are equivalent. So we can factor that out the front. Then we have this term and this term over here with a minus sign. So that's going to be the creation plus the annihilation operator squared minus the difference of the creation and annihilation operators. So that is what these two terms have given us. What about this term over here? Well, we have an EJ and an EJ. Those guys are going to cancel. We have a 2 over 24. That's going to become 1 over 12. So we have minus EC over 12, and then the creation plus the annihilation operator to the power of 4. Now, what can we do with this difference over here? I'm actually going to write it out in full. I'm going to expand this out, and we're going to see how we can manipulate these creation and annihilation operators. So just remember that these are not commuting operators. Commutativity is not guaranteed for operators in quantum mechanics. In fact, it is just a special case that operators commute. So let's have a look at this. I'm going to just look at what's inside the brackets over here. what contributions are we going to get? From this term, we're going to get creation, creation, plus annihilation, annihilation, plus creation, annihilation, plus annihilation, creation. So this is all of the 4 combinations that we can get. And these guys are not the same because we're swapping the order, and the order does matter because these guys do not commute. So what about this term over here? Now we have a minus sign. We have minus creation, creation, minus annihilation, annihilation, and then we're going to have 2 minus signs. The mixed terms are going to get a minus sign from here, and then another minus sign that's going to become plus. So we have plus creation, annihilation, plus annihilation, creation. So let's see what we can cancel over here. These doubles, these like double pairs, they're all going to cancel because they have a minus sign corresponding over here. So creation and creation is going to cancel with minus creation, creation. Annihilation, annihilation is going to cancel with minus annihilation, annihilation. So we're only going to have the mixed terms. So I'll write this underneath. The mixed terms are going to be 2 times creation, annihilation, plus annihilation, creation. So because we have 2 copies, we have 1 copy over here, 1 copy over here, and 1 copy over here, 1 copy over here. So that's what we've got. Now we can do is we can take this form over here and we can flip it around using this commutation relation. So what is that going to be? We're still going to have 2 out the front. We're going to have creation, annihilation. Then I want to turn this annihilation, creation into creation, annihilation. So I'll turn it into this, and then we have to add 1. Now why do we have to add 1? Well, it's because of this relationship over here. So implicitly, what is this actually telling us? I'll write that underneath. This is telling us that if we have an annihilation, then a creation minus annihilation, creation, that is equal to 1. So then all we have to do is just move this to the other side, and that gives us what we have over here. So if we have the lowering operator first, that's the same as putting the raising operator first and then adding 1. So we just move this to the other side of the equation. So that's what we've got, and we can also repackage it a little more. We can see that there are 2 copies of this, and we can pull out a factor of 2, and that 1 is going to turn into a half. So we're going to have 4 times creation, annihilation, plus 1 half. So that's what we've got. And now we can substitute that back into this over here. And this factor of 4 is going to go into the square root. It's going to turn into a 16. So we're going to have 16 on 2, which is 8. So then this prefactor is going to turn into the square root of 8 EC EJ. And over here we're going to have just the creation, annihilation, plus 1 half. So this is just like the quantum harmonic oscillator, where you have some kind of coefficient at the front, then you have this combination of creation and annihilation operators plus 1 half. But we also have this quartic correction. So this is a quartic correction over here. EC on 12 times the creation plus this annihilation, all to the power of 4. So there's a lot of terms involved in this over here. I'm actually going to make a separate video for that. But first, I want to define some more quantities. So let me define some quantities that we can see over here. This term that has a square root, I'm going to define that as omega naught. So omega naught is equal to the square root of 8 EC EJ. So that's a definition. Another definition I'm going to use is delta equals minus EC. And this delta you can interpret as the anharmonicity. Now if something's anharmonic, that means it is not harmonic. And harmonic means evenly spaced energy levels. So what I'm denoting by lowercase delta is actually the anharmonicity. That is the difference or the deviation away from those harmonic, evenly spaced energy levels. So this minus EC over here, I'm just defining as delta. One more thing I also want to write is what this is equivalent to. We can approximate this. This is approximately equal to 6 times the creation annihilation squared plus creation annihilation all plus 3. So this over here is just an approximate form of this guy over here. And in a separate video, I will derive this approximation. I'll show you why this happens. And one approximation that we're implementing over here is we're expanding this out. We're looking at all of the possible terms, and then we're only considering the terms that have an even number of creation and annihilation operators. So we have 2 creation operators and 2 annihilation operators, and they come in different orders. And then we just use this commutation relation to swap these guys around and turn them into this form. So there is a factor of 6, and it multiplies this combination. So this is what we have. We have this approximation for this form. Now what I want to do is I want to write this Hamiltonian using this approximation and using these definitions. So I'll write that underneath. So here's what we have. We have that the Hamiltonian is equal to omega naught times creation annihilation. I'm going to ignore this 1/2 because this 1/2 is, when we multiply by this, is just going to be a constant. And constants have no physical significance. So I'm just going to ignore all the constants. And also over here, we have a 3. That is a constant. If we substitute this 3 in here, we're just going to have 3 times this cofactor, and that, or this coefficient, and that is just another constant. So we're just going to ignore all of those unnecessary constants. So the next term we're going to get is plus delta on 2, and then we're going to have creation annihilation squared plus creation annihilation. So this is what we have. This is an approximate form of the Transmon Hamiltonian. Where did this come from? So this term in the front came from this quantum harmonic oscillator term. And this term over here, because of this factor of 6, this 6 on 12 became 1/2. And this minus sign has been absorbed into the definition of delta. So delta is minus EC, and that is why we have a plus sign over here. And these two terms have just come from this approximation of the quartic term. So this is the square of the creation annihilation operator pair. And then we have another copy of the creation annihilation operators. So I'm going to rearrange this a little bit. I'm going to write it in a slightly different form. This is also equal to omega naught plus delta on 2 times creation annihilation. So that is just taking this term over here and this term, distributing this delta on 2. And then finally, we have that quadratic term. So we have delta on 2 times that quadratic term. Creation annihilation squared. Now what I want to do is I want to define another quantity. I'm going to define omega is equal to omega naught plus delta. So this is just another definition, omega naught plus delta. And if I substitute that in over here, what is that going to give me? Well, it's going to give me this form. We're going to have omega minus delta on 2 times creation annihilation plus this delta on 2 creation annihilation squared. So that is just what has happened. This term has remained unchanged, but this term has changed. Because if you substitute this definition in here, you're going to get omega naught plus delta minus 1/2 of delta. And plus delta minus 1/2 of delta, that's just going to leave plus delta on 2. So we get this half. So this is equivalent to this. I'm just writing it in terms of a more natural quantity. This quantity is more convenient when expressing the energy levels. And finally, we can also write this in an alternative form. I'll write it underneath over here. This is an alternative way of writing that expression. We can write it as omega times creation annihilation plus delta on 2 creation annihilation times creation annihilation minus 1. So have a look at what I've done over here. If you combine these guys together, you get creation annihilation squared. And if you combine these guys together over here, you just get minus creation annihilation. And that minus creation annihilation has a factor of delta on 2 at the front. And you can just move it over and have it join with this term over here. And that's what we have in this definition. Now, the next thing I want to do is I want to express this creation-annihilation pair in Dirac notation. So I'll write this in Dirac notation. So when we see creation, annihilation, we can think of that as a sum over some index. Now, I'm already using I to denote the imaginary unit. So I'm going to use J to denote this index. So we have J, and this is the same as J times the bra version of J, and then the ket version of J. So over here, we have a bra and then a ket. And that is actually very different. This over here, this is not the inner product that we usually see. Usually when we have an inner product, that looks like this. So I'll show you what an inner product looks like. An inner product would look like this. You would have something like psi and then phi over here. So that would be an inner product. But if you have something like this, this is an outer product. And this gives us an operator. So this is a way to construct operators. So you can see it's not that same order that we're used to. It's not this bra-ket order. We still have the bra and the ket, but they're in opposite orders. So this is a way of expressing the creation and annihilation operators in Dirac notation. Now what I'm going to do is I'm going to write the Hamiltonian using this. So the Hamiltonian is, I'll write this below, the Hamiltonian is going to look like this. We're going to have H hat is equal to, I'm going to use this definition of the Hamiltonian. So we're going to have a sum over this index J, and inside over here, what we're going to have is omega minus delta on 2. Then this over here is creation annihilation. So that's just going to turn into J. Then we're going to have delta on 2. And here we have annihilation creation squared. And that's going to turn into J squared. And I'll close this bracket. And then we're going to have a ket J and then a bra J. So this is what we have. And we can actually call this omega sub J. So I'll call this omega sub J, and I'll write that underneath over here. So I'll do that right over here. Omega J, that's the jth omega, or the transition frequency. This is equal to omega minus delta on 2 times J plus delta on 2 J squared. And here we have the approximate form of the energy spectrum for the Transmon qubit. And you can try substituting values of J. You can try substituting 0, 1, 2, 3, and so on. So this is, of course, just an approximation. Everything we do is an approximation, but it is a very decent approximation, especially if we're only interested in the first few energy levels. So have a look at what we've accomplished here. We've started with these definitions of the dimensionless charge operator and the superconducting phase. We wrote them in terms of the creation and annihilation operators. We substituted those definitions into this Taylor series approximate form of the Transmon Hamiltonian. We did some manipulation, and then we found this approximate form for the Hamiltonian. Then we did some redefinitions. We defined these quantities over here, and then we found the energy spectrum of this Hamiltonian for the Transmon. And what is very important to notice is that you don't actually have h bars multiplying over here. That's because we're dealing with dimensionless quantities. There's no h bar appearing over here. But this tells you the frequencies that you need to raise this system from the ground state to the first excited state, and then the second excited state, and so on. So this is what we've got. And we're going to keep dealing with this in later videos in the quantum mechanics playlist. So this is very important. This expression is going to come up in later videos. And then we're going to turn this Hamiltonian into a two-level system Hamiltonian. It's going to become a Transmon qubit. And that has applications in quantum computing. You'll see more of those applications later in the quantum mechanics playlist. You can find other videos if you click over here.